PreAP PreCalculus. We are notes 4.1. This is the third part of the notes. First part we did the fundamental theorem of algebra. Second part we tried to figure out how many of the roots could be positive or negative with Descartes' role of signs. In this part here, we're going to try to determine how many of the roots could be 0. We have three graphs. We have f, we have g, and we have h. What we are supposed to do first is rewrite each of the functions in completely factored form. So this is function f, g, and h. So in f, this is GCF of x. If you factor that out to the front, you're left with the trinomial x squared plus x minus 2. Now this trinomial factors into two binomials, an x plus 2 and an x minus 1. The directions were to simply factor it completely. We have factored f completely. G has a GCF of x squared, leaving us with the binomial of x minus 3. That is completely factored. H does not have a GCF. We can factor by grouping if we group the first two terms together and the last two together. GCF of the first group is x squared, leaving us with x plus 1. GCF of the second group is a negative 4, or a subtract 4, leaving us with an x plus 1. Each of these terms have a GCF now of x plus 1. Factor that out to the front, leaving us with x squared minus 4 as our other binomial. X squared minus 4 is a difference of two squares, so this factors into these three binomials. So what does factoring have to do with finding the zeros of a function? So we're going to try to figure that out here. Based upon the factors, how many times is x a root of the function? And then how is this visible in the graph? So looking at f of x, x is a factor of f of x one time. Therefore, x equals 0 is a root once. How is this visible in the graph? Well, if you look at the graph here at 0, f of x crosses the x-axis without changing concavity. Therefore, x equals 0 is odd multiplicity that equals 1. We knew that going into it. And this is just confirming that if x is a factor once, then it's going to have an odd multiplicity, which means it's going to cross the x-axis without changing concavity. Looking at g of x, how many times is x equals 0 a factor? Or how many times is x equals 0 a root? X is a factor of g of x twice. It's because it is x squared. Therefore, x equals 0 is a root twice. Graphically, g of x is tangent to the x-axis at x equals 0. Therefore, x equals 0 has to be even multiplicity at least 2. I mean, that's just looking at the graph. We know it's actually 2 by looking at the multiplicity here for the exponent. H of x is not a factor of h of x. Therefore, x equals 0 is not a root of h of x. H of x does not contain the origin, which would be where the y value is 0, and the x value is 0, I should say. Therefore, x equals 0 is not a root. So let's try to sum this up. Two of the three functions have something in common, both graphically and analytically. That is different from the other function. What are these differences? Well, graphically, f and g of x have x equals 0 as a root. Analytically, f of x and g of x are missing a constant term, which allows a greatest common factor of x to be factored out. Which I didn't say it explicitly, but that's implying then that h of x does not have x equals 0 as a root, and h of x does have a constant term, which doesn't allow g of x, does not allow a GCF of x to be factored out. Based on what you've just seen, how we determine the number of times x equals 0 as the root of the function just by looking at the equation. X equals 0 is a root n times where x to the n is a GCF. So just by looking at it, ask yourself, what's the GCF? If x is part of the GCF, what's the exponent that you're putting with x and putting out in the front? Whatever that exponent is, that's how many times it's a root. Is it possible that any root of p of x, that any roots of p of x are 0? Now, p of x is a new function. And we would say no. P of x has a constant term of 3, which prevents a greatest common factor of x to the n. Thus, x equals 0 will not be a root of p of x. So to sum up, if you have a constant term, you have no zeros that are 0. You have no roots that are 0. You have no roots that cross the origin. If you do not have a constant, which the first two do not have a constant, then this will have roots that are 0, potentially plural, depending on what the GCF is. The next section that we're going to do, the next part of this section, is determine how many roots can be imaginary. We've done how many can be positive or negative with Descartes' rule of signs. We've just done how many of the roots can be 0, looking at if the constant term exists or not. And then the next part of the notes, we're going to determine how many roots can be imaginary.